Okay, this is the Sp15 update for the phase shift oscillator experiment. I assume that you have the handout, which primarily consists of a couple pages of description about the circuit, and that's where I started. So the circuit we're going to implement is on this page. Okay, you can use 4 op amps or a quad op amp. I chose to use a quad op amp, the LM324, which is essentially a quad 741. So I took that information from the pinouts and I put it on the diagram. And then I wired it up. Pretty small circuit. The key is the capacitors. That's where you're going to take your measurements. So I hooked it up to the dual power supply. Now you're going to use plus voltage and minus voltage with a common. Okay, I set it at the default, which was 12 volts. Let me turn on the unit here, and we see 12 volts operating. Don't need the 5 volt supply, and we're ready to go. Check your currents when you first start up. You can see this is 8 milliamps. 8 milliamps on one side and 7, and on the positive and the negative about the same. That's a good sign that you've probably got things connected. Now the only 2 adjustments we have are associated with the 2 potentiometers. This is the bias potentiometer. Somewhere around plus or minus 1 volt is usually typical. We'll look at the value I ended up with, and then this is the gain potentiometer. So I started out with as I adjusted, I got a good signal, and I'm at minus 0.75 or 3/4 of a volt on the bias. Now the bias has both a plus and a minus connection, so you can adjust it either way. If I adjust it, you can see that the bias voltage can go negative or it can go positive, and we need that capability to get the oscillator running. It's not particularly sensitive to the adjustment. Here I'm at plus 0.82 and I see the signal. If I adjust it down, it still works at minus 3 volts. Once it gets operating, it'll be fine. But I found a pretty good looking signal at around minus 0.75 or volts or so. So you can start around there. Now, the 2 signals I'm measuring, the channel 1, the yellow signal, is the signal that is fed back to the primary amplifier. And I'm measuring that voltage, and I'm also measuring the voltage that is on the output of the first op amp. So those are the 2 values that I'm measuring on the circuit. That is this point here, and the second point is after the amplifier. Okay, so when we look at the signal, this is what we see. The frequency is 1.534 kilohertz. Right, very close to the calculated value. Look in the handout. Now in this case I have a phase shift of minus 135 degrees or 135 degrees. That includes the 180 degrees of phase shift from the op amp, the negative feedback op amp, and the 45 degrees from the this RC network. If I move back to this pin here, so now we see the phase shift has changed to be 90 degrees between those 2. One of the unique parts about this circuit is that you can generate sine and cosine signals. So that's a sine and a cosine function. I'll move that point back as the point of reference is that input op amp. So there we see. Now to get started in adjustment of the gain, what I did was measure the output of this op amp and just adjust it for a good looking sinusoid. So as I adjust the gain pot, you'll see it's fairly sensitive, but I adjusted it till I got a pretty good looking sine wave. If I have too much gain, you'll start to see some distortion creeping in. You can see it on the blue signal in particular here. That means the op amp's having some trouble with that signal. So I just backed off from that point until I got a pretty good looking sine wave on the setup. So I adjust that till I get a good looking. Alright, so now we have that's the first set of op amp. I'll move to the next point, and we see the phase is now almost 90 degrees or minus 88 degrees. The next point, we'll see another 45 degrees of phase shift and come into that point, and we see 43 degrees of phase shift. And then we get the final value. So the amplifier is very straightforward in that way. One of the easiest oscillator circuits you will ever design and build. Of course, it's very low frequency, only just slightly over 1.5 kilohertz. So that's the lab update. Now, once you have the oscillator working, I'd like you to compare the oscillator to the fixed oscillator. So I've got my Regal oscillator operating here. It's at 1.574 kilohertz. Okay, magnitude doesn't matter. I did turn on the output. Remember to do that. Now, when we look at the two signals, you'll see the one signal is moving to the left. That's actually the ARB generator. Now, this means that the frequencies are not exactly the same. So I'm going to adjust the frequency of the ARB. If I adjust it higher, then the wave moves faster because the delta frequency is changing. But if I slow it down, you'll see that you can come to a point where the oscillator, the two signals are almost the same frequency, no change at all. That turns out to be 15736 kilohertz, 1.573 kilohertz, and it drifts a little bit. These oscillators are fairly sensitive to a variety of factors, temperature, leads, all kinds of stuff. When you play with this, you'll see that it's pretty sensitive. Normal oscillators are in temperature controlled environments to make sure that all the components are staying at a nice stable point. But you can see the oscillations staying pretty steady, right? Now, once you have done this test, then you can go through and compare various differences between the fixed oscillator, the ARB, and your own oscillator, sine wave oscillator. That's the main part of the lab.